Math 287, Quest to College. I'm Joe Vasta, and we're going to cover 9.5 Vector Differential Equations, Defective Matrices, or we can call it Systems of Differential Equations. Now in 9.4 we covered non-defective matrices. 9.5 covers defective matrices. Our system of differential equations is still homogeneous, and so this is what it looks like, and we'll put up an example. So we have vector x prime equals a times vector x, and there's the matrix there, 2, -1, 4, 6, and we are trying to solve this system of differential equations, or this vector differential equation, and our solution, since it's a 2 by 2 matrix, is going to look like this: C1 times vector x1 plus C2 times vector x2. And what we said in the last one is this vector x1 is going to be e raised to the eigenvalue times t, and then that's going to be multiplied by an eigenvector of that eigenvalue. And so x2 was going to be similar. But look what happens here, and probably from the title you're going to guess this. So when you find the eigenvalue eigenvector pairs of A, you just have one eigenvalue, which is 4, and the eigenvector is 1, -2. So 4 has algebraic multiplicity of 2, and it also has geometric multiplicity of 1, which makes the matrix defective. So how are we to do this, and why am I doing PowerPoint for an example? Because I'm going to run through some procedures, and then we're going to streamline it, and then the rest of the lecture will be done on a piece of paper. So x1 we can say is e to the 4t times any eigenvector, which we'll pick 1, -2. But what's x2? We don't know. So before we get into this, let's remember that a times v equals 4 times v, okay, because that's the definition of the eigenvalue eigenvectors. And 4 is an eigenvalue and v is an eigenvector. So let's go ahead and take a guess. Maybe a guess for x2 would be to put an extra t next to this solution right here, because we did that with single differential equations. Shouldn't it work here? Let's see if it does work. If our guess is good, then x2 should satisfy the vector differential equation. In order for it to satisfy the vector differential equation, we're going to go ahead and plug x2 into this vector differential equation. So before we plug it in, we need to find the derivative of this. The derivative of x2, it's a t e to the 4t, so you're going to have to do the product rule. V is a constant. So that's what we have when we do the product rule. V is a constant, and you have the derivative of the first times the second plus the first times the derivative of the second. And I'm going to plug x2 prime and x2 into this vector differential equation. So there's the vector differential equation with x2 plugged in there, and look what we have. We have, the x2 prime became this, that's what we found, and then we have A, which I didn't write out what A was, and that's all right, I don't need to, it's just that matrix up on the top left. And then we have x2, which is t e to the 4tv, we have that right there. So what do we have here? Let's go ahead and look at our next step. Our next step is we are going to replace this AV with 4V. Now, how did I do that? I factored the TE to the 4T out front. I went ahead and made this replacement with the AV equaling 4V, and then I put the TE to the 4T back in there. So that's what I did. I went from here to here. It almost looks like the same equation, but it's not, because the A is replaced by the 4 because of this rule here. So the next thing I'm going to do is I'm going to make the realization that I have a 4t e to the 4t v on both sides of the equation, so I will subtract that on both sides. And so I have e to the 4t e to the 4t times v equals 0. Well, e to the 4t could never equal 0, so v would have to equal 0. And v equaling 0 is telling me that my eigenvector is 0, but by the definition of an eigenvector, it cannot be 0. This gives us a contradiction. So our guess was bad. This is terrible. So when you do your homework, you're not going to go ahead and do your homework problems this way, because why would you want to go down a dead end with a contradiction? So we're going to go ahead and make another guess. My next guess is actually going to be my old guess plus something else. So let's go look at that. So here's my old guess, t e to the 4t v, and then I'm going to go plus e to the 4t times a new vector u. So this is the new u. Yeah, that's right. This is self-improvement here. I'm going to go ahead and plug x2 into our vector differential equation, just like I did when I made this guess. But in order to do that, I have to take the derivative. There's going to be a product rule on the first term, and then the second term is just going to be some chain rules. So here's the derivative of x2. And the derivative is with respect to t. So the first two terms are a result of the product rule. In fact, those first two terms are the same ones you see there. And then you have 4e to the 4t times u. So here's the vector differential equation. And I plug this part where the red dot is next to into the left-hand side, and then I write a times this x2. So it looks pretty intense. Okay, it looks a lot intense. I'm going to go ahead and distribute that a into the terms on the right-hand side. And so I have that right there. And then what I'm going to do is I'm going to go ahead and color code things. So I've written all the terms that have just an e to the 4t in blue, and then I wrote the terms that have a t e to the 4t in red. And this might remind you of partial fraction decomposition. I'm going to set the blue ones equal to each other in their own equation, and the red ones equal to each other in their own equation. And so when I do the red ones, I have 4t e to the 4t v equals a t e to the 4t v. Now, what I can do is divide both sides by t e to the 4t. But before I do that, here's the blue equation. I'm sorry, here's the blue equation. And so I'll do that, and I get 4v equals av, which is exactly what we have here. So this is a good thing. We didn't get a contradiction on the red part. Now over here, I know I kind of jumped the gun there. I'm going to divide everything in this equation by e to the 4t, and I get v plus 4u equals au. So getting back to the red side, I'm going to go ahead and take everything on the, I'll put the 4v on the right-hand side, write that as 4iv, factor out of v, and then, put everything on the left-hand side. So I'll do some algebra. We saw this earlier when we were looking at eigenvalues, eigenvectors for the first time. And I have a minus 4i times v equals 0. And this is actually how you find the eigenvectors. You do that, you find the null space of a minus 4i. Well, I'm going to kind of do some of the same thing over here. I'm going to leave v on the left-hand side, bring the 4u to the right-hand side, write that as 4iu, factor a u out, and I'll end up getting v equals a minus 4i times u. And I'm going to change that around so you could verify the algebra. And so it looks like this guess does work. And you would actually find the u by putting this into this linear system and solving for it. So yes, we can find the new u, and that's what all of 9.5 is, the search for the new u. And so our answer then would be this right here. Here's C1. here's x1, which is what we would normally have guessed for that. And then plus c2, here is what we would use for our x2 vector. And there's the u right there, which is in bold. So if you're saying, I don't know if I can do a problem, that's how you should feel right now, because this was very theoretical, even though it was on a specific example. We're going to go to the paper. I'm going to do this example by hand, because I really haven't found the new u, and show you that I'm not going to write all this stuff down. We're just going to go ahead and show you how to do the problem so you'll know how to do these problems. So this ends the PowerPoint part of this lecture. Let's go ahead and do this problem. So in your homework, they're going to have you solve these vector differential equations with defective matrices. So I'm going to actually do this problem from scratch so you can see what happens here. So I'm going to go a minus lambda I is 2 minus lambda negative 1 4 6 minus lambda. And then I'm going to go ahead and find the determinant. To find my eigenvalues, I'll set that equal to 0. So I have lambda squared. This is going to be minus 8 lambda. And then I have plus 12, and then minus a negative 4, so that's going to be plus 16. Set equal to 0. This factors into lambda minus 4. Quantity squared equals 0. Lambda equals 4. Has algebraic multiplicity of 2 because we have that right there. I'm going to go ahead and find the eigenvectors. How do I find the eigenvectors? Well, what I usually do is I go ahead and write out this. I say a minus lambda I, and I'm going to go ahead and plug a 4 in there. So this gives me negative 2, negative 1, 4, and then we have 6 minus 4, which is 2. Now I'm going to write things out a little more officially than I was writing things out. When I do this, I always put red dots there. Okay, when I first did it, I didn't do that. What I'm really doing is I'm trying to find the eigenvectors, which lots of times we call V. And we're actually solving that system. Now I don't write that down every time, but I am going to write it down this time because I think this is going to be important to see. And then, you know, I put some zeros there. So that's what this system becomes. Okay, so we can see that this matrix has 2 rows that are just scalar multiples of each other. So I'm going to write the first row as 2, 1, 0. And then the last row as all zeros. Here's x, here's y. And so y equals t, 2x plus t equals 0, 2x equals negative t. And then we have x equals negative t over 2. So my eigenvectors look like this. They look like negative t over 2 t. Or I could actually write them as, take out a negative 1/2, I can write it as a t comma negative 2t. Okay. Now that was just a matter of style. I didn't need to do that. I wanted to match up with what I had in the PowerPoint. If I factor the t out, then I have eigenvectors that look like this. They look like t times 1, negative 2. Okay? And so we see that there's only one parameter here, which means we have geometric multiplicity of 1, which means A is defective. Okay, great. Perfect. So A is defective. So what are we going to do now? Everything I've done in this problem up to now has just been what we've been doing in linear algebra. So let's go ahead and write up part of the solution. Maybe we can look at our solution here. So this is a 2 by 2 matrix. So my solution is going to be x bar equals C1, and then I use this eigenvalue, e to the 4t times the eigenvector, or any eigenvector, and I will go 1, -2, plus C2 times. Okay, so now we're thinking about what happened on the PowerPoint. And on the PowerPoint, what we did is we went T e to the 4t times 1, -2. In a perfect world, that's what it would be. I'd put another parenthesis and say, there, that's how you do these problems. But it wasn't a perfect world, and when we did that, we got a contradiction. And we found out that we can go plus e to the 4t times the new u. Here's the new u. So we don't know what that u is. But here's the deal. When you figure out what that new u is, then you've got your answer right there. There's the answer. So how do we figure out what the new u is? Well, let's go back to this. Remember how we had this equation and we found the null space. And if you remember back to the PowerPoint, we had another equation that was a minus lambda I. And I think in the PowerPoint it's a minus 4i, which is, that's what it is. Here's 4, but I'll just go a minus lambda I. And then we had this written. This is how you find the new u. U equals v. So this was the derivation that we did. So it kind of looks like this, except now we know what v is, and we're going to put a u there, and we're not going to put 0 there, but now we're going to put v there. So when we did this, we wrote this matrix when we did the one up here. But now what we're going to do, this matrix that we're going to write, is we are going to put the a minus lambda I, which is -2, -1, 4, and 2. And now instead of putting 0, 0 there, because there was a 0 there, we're going to put our eigenvector that we used right here. So I'm going to go ahead and put a 1, -2 there. Now technically I'm looking at this and I know that a minus lambda I does not equal this matrix with the zeros. So you know what I'm going to do? I'm just going to, because you might be looking back on this and saying, well, why did he put that? I'll just put a colon there. I panic and then I abuse punctuation, and that always got me in trouble in the English classes. Okay, so now I'm going to solve for this, and if I can find a solution for this, then I have found my new u. So once again, you can see that both rows are multiples of each other, and I'm going to go ahead and write the first row as 2, 1, -1, multiplying that by a -1, and then I'll zero out the second row. Here's x, here's y. So now it's going to look very familiar to this. You're going to see kind of the same thing. So that's what I'm going to do. I'm going to say, well, let's let y equal t. And the first equation says 2x plus t equals -1. So 2x equals -t minus 1. X equals -t minus 1 over 2. Okay, so here's my x and here's my y. Now here is the sweet part about this. The sweet part is there are infinitely many different choices of new u's that you can put there, and any one of them will work. Now, some of you are like, well, what about when u is 0? You can never have it a t-value that will zero out both of those values, so you can never have that. So I think an easy t-value would be t equals 0. If you have t equals 0, then your new u, and we'll write it as a column vector. What's x? X would be -1/2. Whoops. And y would be 0. And so, some of you do not like that t-value because you see a fraction there. Some of you would have chosen t equals 1. So let's just do that in red. I'm not saying this is wrong, but if you had chosen t equals 1, you would have got your u to be -1, and the other one would be 1. If you chose t to be -1, you would have got 0, -1. Okay, so there's infinitely many new u's you can pick, just like there's infinitely many eigenvectors you could have originally picked right here. But once you pick those guys there, you've got to use those in this setup right here. So let's go ahead and write up our answer then. Our answer's right there, so all I have to do is put this guy right there. So this is just me writing out what I have a box around. C1 e to the 4t, 1 -2, plus C2, we have t e to the 4t, 1 -2, plus e to the 4t, and then I'm going to go ahead and put the -1/2, 0. And it's hard to believe that, that you could put the -1/1 there and you would still have a legitimate answer. So that is how we do these problems. Well, by the way, this guy was a u. U has a name. It's not just the new u. U is a generalized eigenvector of your matrix A for lambda equals 4. Okay, so notice I said generalized eigenvector. It is not an eigenvector, but it's called a generalized eigenvector, and that's just what they call it. Okay, so we are done with this problem. Are we really done with this problem? Some of you might say, well, Joe, I would like to compact this answer, and that wouldn't be wrong to do that. So I am done when I have boxed it, but I'm going to just show you something that some of you want to do because, it's going to look a little nicer. 1 -2. It's the first part of the answer. And then, look what these guys have in common. They have an e to the 4t, which I can factor out front. So I have C2 e to the 4t. And then I can just say, look, I'll read the top row here. I have t -1/2. And then on the bottom we'd have -t. No, on the bottom we would have -2t. So there is another legitimate answer. Now, if it's just making you really mad about that -1/2, then I'll show you what to do after. But let's go ahead and say you just did your homework problem and you got that. And the book goes ahead and gets this, C1e to the 4t, 1 negative 2, plus C2e to the 4t, and then they got t negative 2t minus 1. And you're looking at this, and you're really sad. Okay, well, don't be so sad, because on the test, first of all, this wouldn't happen unless somehow you had the answers. But when you're doing your homework, before you throw your homework away, you might have the right answer, and you might have just got a different parameterization of the curve. So curves can be parameterized many different ways. And to check to make sure these are the same curve, this is what I'm going to do. It's going to remind you of re-indexing. I'm going to replace every t with, so I'm kind of looking at this, and I would really like to have a t minus 1/2 up top. So t minus 1/2. So when I do that, and I'm just focusing in on this now, I have a t minus 1/2 on the top, and then I have a negative 2 t minus 1/2 minus 1. And I should get to what I have. You could have gone the other way as well. You could have done something different and try to replace something up here to get one of the components and then see if the other component matches. So I have a t minus 1/2 there. And on the bottom I have negative 2t plus 1 minus 1. Those are out of there, and look, I have the answer. So I just went ahead and verified that this and this, those are just different parameterizations of the same curve. So that is what you can do. This is a correct answer. This is a correct answer. Perhaps the book got this answer by letting t equal negative 1. And yeah, I think that's what they did. They let t equal negative 1 up here when they were looking for the new u. Okay, one last thing, and I know we were finished with this problem when I boxed that answer there, but there's one last thing that I want to do, is to address the fact that you might be mad that there is a negative 1/2 there. Another thing you can do to get rid of that, if you're not happy with that, most people are just happy and they just move to the next problem, is you could multiply the top part and the bottom part by 2. So if you do that, you end up having 2t minus 1, and then on the bottom I'd have a negative 4t. And then this is an e to the 4t. And now the c2 is actually a different c2, so I'll just go ahead and put c2 there. And what you really did is you factored out a 1/2 from both of these, and then let that scalar be absorbed into the constant. So that is what you did. And you can see that these are just scalar multiples of each other. That's acceptable. It would pass the test. It is just a different parameterization of the same curve. Maybe you're changing the speed of the bug on the curve. But this is also acceptable. But we may have said too much about problem number 1. I think we should do a few more problems and see how this goes. So when you do your homework, I think the main thing, what is the main thing, is you have to learn how to find your new u. You know, it's written like this, and you find your new u by not finding the null space of A minus lambda I, but putting that in a matrix and putting your eigenvector there, and that will find you the new u, and this will always work. Let's go ahead and do another problem. And here it is. 11, negative 25, 4, negative 9. Okay, so the first part of this problem is linear algebra. A minus lambda I, we have 11 minus lambda. We have negative 25, 4, and negative 9 minus lambda. I'm going to go ahead and do the determinant up here this time. A minus lambda I. Take the determinant. So I'm going to get lambda squared. Minus 11 lambda plus 9 lambda, so that's minus 2 lambda. And then I have minus 99, but a minus negative 100. So minus 99 plus 100 is plus 1. Set this thing equal to 0. This factors into lambda minus 1 quantity squared equals 0. This problem's going to go faster because I'm not going to say all those things at the end. We'll get the answer and move on. Okay, so we know that lambda equals 1 has an algebraic multiplicity of 2. Now to find the eigenvectors, I go ahead and I'll write this out even though it's not necessary to write this out. A minus lambda I. I'm trying to find these eigenvectors, so that's what I'm trying to find. This equals 0. So that's not necessary to write. So this is going to give me, I'm going to plug 1 into this matrix. This will give me 10, negative 25, and then I have a 0 there. And then 4. And I'm plugging 1 in there, so I have negative 10, 0 as well. Both of those rows are multiples of each other. You can see that, hopefully you can see that. You can multiply the bottom by 10 and the top by 4. Yeah, and you can see they're the same row. So I'm going to go ahead and reduce this. So the last row will be zeros, and I will take this and divide by 2. So I'll do some row operations here. And I'm going to find the eigenvectors associated with lambda equals 1. And you know what? Since I'm just going to eyeball this one, the eigenvectors look like this. They look like v equals, see, I'll zero out that first row by letting x equal 5 and y equal 2. So any multiple of 5, 2 will work. The geometric multiplicity is 1. A is defective. Okay, and that's the section we're in. We're in defective matrices. So my answer, so I could actually almost write up my answer, and that's what I'm going to do. So x bar equals, I have a 2 by 2 matrix, so I'm going to have 2 CIs. The first one is going to be C1, E, go to the eigenvalue, 1t, and then the eigenvector, 5, 2, plus C2. Now this is a little memorization here. We have t e to the t, 5, 2, plus just an e to the t. And do you remember what we were calling this guy right here? We were calling that the new u, which is blue. I feel like Dr. Seuss now. So we just have to find a u there. So one strategy is to just guess. Hey, let's guess. The answer is 4, 5. And that's a bad strategy because you're probably going to get the wrong answer. So to find the new u, I'm going to actually do my work in blue ink. So I've kind of gone this way and done this. You know, if someone's just looking at the PDFs, they might get a little confused at what happened here. Oh well, who cares? So here is the equation. It's a minus lambda I. Here's u. There you are, and then we have v there. So it looks like this equation, kind of. Okay, so a minus lambda I, we know that's 10, negative 25, 4, negative 10. So basically you're just writing this matrix, and instead of having 0, 0 there, you're going to have your eigenvector of 5, 2. So I'm going to go ahead and write that. So this is 10, negative 25, 4, negative 10, and then I'm going to go ahead and put the 5, 2 here. Now, if I decided to put 10, 4 here and 10, 4 there, then I'd have to put a 10, 4 there. Okay. Let's go ahead and, well, we recognize that both of the rows, they're multiples of each other. And so when I go ahead and do this, I'll take the last row and I'll scale it down. 2, negative 5, and 1. And then one of the rows got zeroed out, and we have an x here and a y there. So y equals t, okay? Because it is a free variable, so remember this, we used to write that all the time. And then we have 2x minus 5y, 5t, equals 1. So I solve for x, x equals 5t plus 1 all over 2. So here's my x and here's my y. So the question is, what value of t do you use? Well, the easiest value of t is t equals 0. And some of you won't like that. You'll be like, oh, I don't want to have a 1/2 because isn't that like what we had in the last problem, a negative 1/2. So whatever, make your t equal pi if you'd like. I'm going to actually be courageous and let t equal 1. And I'm going to get my x to be 5 plus 1. That's 6 over 2. So x will be, what did I say it was? 6 over 2, which is 3. And then y will be 1. But if you like, you could put t equals 0 and make it be 1/2 for the x coordinate and 0 for the y coordinate. I believe that's what I have in my notes, but it really doesn't matter. And there's my answer. So I've now completed the problem. I'm not going to, I mean, you know, some of you are like, can you pull out an e to the t and write this as c2 e to the t and then times the vector 5t plus 3, and on the bottom you would have a 2t plus 1. Yeah, you can do that, make it look pretty, but you don't have to. Okay, so let's go ahead and do another problem. Okay, we have a 3 by 3 matrix, and what are we going to do with this 3 by 3 matrix? We're going to find the eigenvalue eigenvectors, and that's the first part of this. So now you might be thinking, what are we doing, Joe? I mean, it doesn't even feel like we're doing differential equations. We are solving, I think our original problem asked us to solve x prime bar equals ax bar. I mean, that's what we're solving there. And remember, I mean, we can write this out. We could say that like x1 equals 5, x1 prime equals 5x1 minus 4x2, and x2 prime equals 1x1 plus 2x3, and x3 prime equals 2x2 plus 5x3. And we can write out the 3 differential equations, but we don't have to, and everything's all compact with the matrices. So what we want to do is we want to go a minus lambda I. Write out what this is. So this is going to be 5 minus lambda, negative 4, 0, 1, negative lambda, 2, 0, 2, then we have 5 minus lambda. Okay, the next thing we want to do is we want to figure out the eigenvalues by taking the determinant of that and setting it equal to 0. So what do I want to do? Maybe I'll just go across the first row. There we go. There's my red arrow. And so I have 5 minus lambda, which is in the positive position. And then this is multiplied by, okay, I'm taking the minor, so this is lambda squared minus 5 lambda. And then we have minus 4. Then the next one is going to be negative 4, which is in the negative position, so there's 2 negatives, so that's going to be a positive 4. And then I'm going to go ahead and find out the minor of this. This is going to be 5 minus lambda, and then there's just going to be a 0 there. 5 minus lambda. Okay, so what do we have? I'm going to make a line go like that. We have 5 minus lambda, lambda squared minus 5 lambda minus 4 plus 4, and then we have 5 minus lambda. Now because I see 2 occurrences of those, and there's 2 terms there actually. Here's your first term, and there's your second term, and each of those 2 terms has a 5 minus lambda. So instead of multiplying that through and writing out 6 terms, I'm going to factor out a 5 minus lambda from those 2 terms, this term and this, and the 4 there. So look what I have. I have lambda squared minus 5 lambda minus 4 plus 4. So this is 5 minus lambda, and then, oh, look at that, the 4's cancel, and I have lambda squared minus 5 lambda. So I'm going to factor a negative out of that first one, so this is negative lambda minus 5, and then over here I'm going to factor a lambda out, lambda minus 5, and so this gives me negative lambda, rearranging things, and then we have lambda minus 5, quantity squared. I'm setting that equal to 0. I get lambda equals 0, and lambda equals 5. Those are my 2 lambda values. So now what I'm going to do is go find the eigenvectors associated with those guys. Lambda equals 0 has algebraic multiplicity of 1, as you can see right there. And I'm going to go ahead and write out the A minus lambda I matrix. And I'm finding the null space of that. So I have 5, negative 4, 0, 1, 0, 2, 0, 2, 5. So when lambda is 0, your A minus lambda I matrix is really just matrix A. And I'm finding the null space. And normally I put like red dots there, but I'm not going to this time. So what am I going to do? I'm going to do some row operations here. I have 1, 0, 2, 0. Multiply middle row by negative 5, add it to the top row, so I'm going to get 0. Then negative 4, negative 10, and 0. And then the last row is 0, 2, 5, 0. Okay, because I am dealing with eigenvalue eigenvectors, I know that one of the rows is going to 0 out. And you can see the last 2 rows are multiples of each other. So what I end up getting for this is 1, 0, 2, 0, 0, 2, 5, 0, and then all zeros. So here is x, y, z. Okay, z is free, so I have z equaling t. I'm going to do something a little courageous here, and I'm going to let z equal 2t. Why? Because the second equation is going to say 2y minus 5 times 2t, so this is going to be, or sorry, plus 5 times z, so that's going to be 10t equals 0. So on this one I'm going to get y equals, bring that over, divide negative 5t. And then of course from the first equation x is going to equal negative 4t. So it looks like I have, oh, I almost did that mistake where I wrote the z first. So I have negative 4t, negative 5t, then 2t. And so I don't like all those negatives, so I'm going to scale it so it says 4, 5, negative 2. Okay, so the next one that I'm going to find is lambda equals 5, which has algebraic multiplicity of 2, because we have the 2 right there. By the way, this one has geometric multiplicity. This eigenvalue of lambda equals 0 has geometric multiplicity of 1. Algebraic multiplicity equals geometric multiplicity there. We're thinking it's not going to happen here because we're doing the section called defective matrices. Let's go ahead and put 2 where? Into the A minus lambda I matrix. And we're going to find the null space of that. Now if you're wondering where the A minus lambda I matrix went, it's right there. So this is going to give me 5 minus 5, 0. Then negative 4, 0. And the next one is 1, negative 5, 2. And then the last one is 0, 2, and then 0. So when I go ahead and, and I'm going to go ahead and find the null space there. And I can see that row 1 and row 3 are scalar multiples of each other. I'm going to go ahead and write row 2 as the new row 1. So this is 1, negative 5, 2, 0. Who would have thought that doing differential equations meant doing mostly linear algebra? So that's why we kind of have these both in the same class, because they are related big time. Once again, it does not feel like we're even solving a system of differential equations, and we are. So here's x, here's y, here's z, and then we're going to go through the whole little game here doing this again. So what do we have? We have z equals, okay, so sorry, I kind of slowed down on that. Z equals t, and y equals 0, and x equals negative 2t. So it looks like this is going to look like this, negative 2t, 0, t. The vector that I'm going to pick for this one is, I could pick negative 2, 0, 1, and it doesn't really matter. This is just a matter of choice. 2, 0, negative 1. I could pick any multiple of that, or any t value. And, if t is negative 1, that's what I get. This has, because there's only one parameter, geometric multiplicity of 1, and the algebraic multiplicity was 2, so A is defective. Okay, but now I can already write down the solution almost. Okay, so this right here was lambda equals 0. And then this right here is lambda equals 5. Okay, so let's go write the solution down. The solution equals, okay, because it was a 3 by 3 matrix at the beginning, I'm going to have a C1, C2, C3. And so here's the first one. C1, e to the 0t. So I'm not going to put that because e to the 0 is 1 times this eigenvector. So C1, and then we have 4, 5, negative 2. Okay. Then we're going to have plus C2. And now I have this guy right here, so I can use him. I'm going to go C2 e to the 5t times its eigenvector, which is 2, 0, negative 1. And I select one of those. And then I have plus C3. And this is where I'm going to have to do that thing that I was doing before. This is big parenthesis t e to the 5t. So this is the 5t because this is where the defective matrix thing breaks down. And then I have this eigenvector, not the 4, 5, negative 2, but the one that belongs to the eigenvalue of 5. This is 2, 0, negative 1 plus e to the 5t, kind of running into this right here. And this guy right here, in blue, this is the new u. But you can see that most of this problem that we've done so far, we're not finished yet, but most of this problem is doing linear algebra. I could have cut through that lambda equals 5. That's not part of the answer. Okay, so let's go ahead and find the new u. Now, how do I find the new u? I use this matrix right here, because this is the one that I used for lambda equals 5, and I have a 5 right here. So I'm using this matrix here. I need another piece of paper. And so what I'm going to do, so let me just cover that up a little. I'm going to go ahead and write down this matrix, which is 0, 1, 0, negative 4, negative 5, 2, going by the columns now, and then we have 0, 2, 0, and then instead of putting 0, 0, 0 there, and that's how I find the eigenvector of 2, 0, negative 1, I'm going to actually now put the 2, 0, negative 1 there. 2, 0, negative 1. This is how I find the new u. Now, is it true that I can write, I didn't write all that stuff down that I did before, but, you know, in this one right here, this was a minus lambda I times v equals 0. That's that one right there. And then this one right here is a minus lambda I. The one I'm trying to find is that one right there, u equals v. And so that's what I'm doing right here. Okay, so I'm covering up the answer, but that's all right. I want to show you that this is going to be very similar. This equals, or is row equivalent to, you can see that row 1 and row 3 are scalar multiples of each other, and I'm going to go ahead and write row 2 first. So 1, negative 5, 2, 0. Oh, I'm not using blue ink. Okay, that's all right. 0, 2, 0, negative 1. And then we zero out one of the rows. Here's x, y, z. I'm going to let z equal t. You know, last time I let it equal negative 2t or whatever. I let it equal t. Oh, no. What did I do last time? Yeah, I let z equal t. I don't know what I'm talking about here. And then I let y. Oh, I'm thinking of the other eigenvalue. Okay, so y is 0 from the second equation, but it's not 0. Okay, so I take that back. So what does the second equation really say? The second equation right here says 2y equals negative 1. So what is y going to equal? Y is going to equal negative 1/2. Okay, so z is t, y is negative 1/2, and then x. So let's move on here. We have x, the first row, minus 5 times y plus 2 times t equals 0. So I have x equals negative 5 halves minus 2t. Okay, so my new u, that's what I'm looking for. What should we set t equal to? Well, why don't we just do it the easy way this time, t equals 0. If I set t equal to 0, I have x is negative 5 halves. I have y is always going to be a negative 1 half. And z is going to equal 0. Okay, so what am I going to do with that u? I'm going to put it right here. So the new u goes right there. So this is negative 5 halves, negative 1 half, and 0. And there's the answer. And that's how you do these problems. A lot of this problem is just doing linear algebra. Can you factor out an e to the 5t? Yes. If you really don't like those fractions, you can also factor out a 1/2 on there and get something that looks kind of pretty. But you don't have to. This is good enough for this class. And this is just an introduction to systems of differential equations. Let's go ahead and do the next problem. So problem number 4. So problem number 4 looks like that. That's our matrix there. And we're trying to solve the system of differential equations. Vector x prime equals a times vector x. And the first thing we do in all these problems is go a minus lambda I, which happens to be negative lambda, 0, 1, negative 1, 1 minus lambda, 1, negative 1, 0, 2 minus lambda. I'm going to go ahead and find the determinant and set that equal to 0. And so when I do that, I'm going to go ahead and travel, obviously, down the middle column, okay, using my purple arrow there. And so 1 minus lambda is in the positive position. And what do I have here? I have lambda squared minus 2 lambda. I'm computing the minor, going AD minus BC, and then I have, what do I have here? I have minus a negative 1, which is plus 1. On the first part, I'm going to factor a negative out of there, so it says negative lambda minus 1. And on this one, I see that this is really lambda minus 1 times lambda minus 1. So this is negative lambda minus 1 cubed. Lambda equals 1 with an algebraic multiplicity of 3. Okay, so that's cool. So what I'm going to do is, I'll write this out this time because I know some people were probably sad that I didn't on the other one. So a minus lambda I times the eigenvector equals the 0 vector. So I'm going to try to find that. That's finding the eigenvectors. And to do that, I'm going to go ahead and put 1 into this matrix. And when I do that, I get negative 1, 0, 1, negative 1, 0, 1, and negative 1, 0, 1. Okay, and then I zero out that because there's a 0 there. And I'll go ahead and do the row operations for you so you don't have to worry about that. I ended up getting 1, 0, negative 1, 0, and then everything else was zeros. That was kind of a joke, but I don't think things are funny now these days in America, are they? And then if you are trying to be funny, then people look at you like, hey, why is your mask upside down? I'm gonna call the sheriff on you, or whatever, I don't know. So look what we have here. We have z equals t, and because it is free, and y is also free, so y equals s. And then what does x equal? X equals t. So basically your eigenvectors look like T, S, T. Or you can look at it like this. This is S times 0, 1, 0 plus T. This is 1, 0, 1. And the eigenvector cannot equal the 0 vector. And so there it is. So it looks like your algebraic multiplicity is 3, but your geometric multiplicity is 2, which makes A defective. Everything I've done on this page was linear algebra stuff that we've learned a long time ago. And now I can write out my solution. So what does my solution look like? My solution looks like this. It looks like C1 e to the, okay, my eigenvalue is 1, so 1t. And then I grab on to one of the eigenvectors, and I'll grab onto this one. 0, 1, 0. Plus C2 e to the t, because I have another eigenvector that's independent from that one. And so I'm going to write this one as 1, 0, 1. And then I have plus C3, and we have this, t, e to the t, and then I go ahead and put an eigenvector there. Okay, so this is what's a little tricky. What eigenvector do we put there? And then we're going to go plus e to the t, and this guy right here is the new u. That's going to be our answer. So you might go, well, okay, so let's label this as the new u. And then in purple, I'm going to say, well, this is an eigenvector. But is it just any eigenvector? And the answer is no. Because some of you are like, can I just go eeny, meeny, miny, mo, and then just like close my eyes, pick one, and put it there? No, you can't. And so what I'm going to do is I'm going to go back to this right here. And that is the most general eigenvector. And what I want to do is I'm considering the A minus lambda I u equals the eigenvector v. So that's what I'm considering now. Remember, before I considered that. So when I do that, I don't know what eigenvector I'm going to use. So I'm going to do this part in purple. So the A minus lambda I is this. Negative 1, 0, 1. Negative 1, 0, 1. Negative 1, 0, 1. Now be prepared to be shocked. I'm going to just put both this t, this s, and this t in there. So let's do that. So this is t, s, t. So what I'm going to do now is I'm going to make the realization that row 1 and row 3 are the same. And so here is, we zeroed 1 out there. And I'm going to subtract. That's what I'm going to do. I'm going to go row 1 minus row 2. So the first one's just going to be this right here. And I'm going to subtract. So I'm going to get a 0, because negative 1 minus a negative 1, and a 0 minus 0, and a 1 minus 1, so those are all zeros. And then I have a t minus s. So look what happens here. This right here is a linear system, and this linear system has to have a solution. And it just so happens, look at the second equation. It says 0 equals t minus s. And so for us to have consistency, what do we have to say about t and s? They have to be the same. That s has to equal t. So when we're making our choice for the eigenvector, we have to have s equaling t. Now they both can't equal 0, but maybe an easy one would be to let s and t, let s equal t equal 1. And what do you end up getting? You end up getting 1, 1, 1. So that's the one I'm going to go with. Is 1, 1, 1 an eigenvector of the eigenvalue 1? Absolutely. This represents any eigenvector. And so we put 1, 1, 1 there, and if we had put 0, 1, 0 or 1, 0, 1 in there, you would have ended up, when you went to solve for the new u, getting an inconsistent system. So there are going to be some in your homework like this, and sometimes you don't want to use that one. Sometimes it says S has to be 0 and T could be whatever. So sometimes you will pick one of these, but it all depends on what this gives me. Okay? So now the rest of this problem is what you think it's going to be. So I'm going to go ahead and do this again, and I'll do it in blue ink. And I write the -1, 0, 1, -1, 0, 1, -1, 0. It's like I'm counting sheep here. Some of you have already fallen asleep. And now I'm going to go ahead and put 1s in for T's and S's. So 1, 1, 1. This is going to give me my new u. And so all the rows are equivalent. So I get -1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0. Here is X, Y, Z. Z is T. Y is S. And X is, oh, so this is negative, and before I think I fixed that, but that doesn't matter. X is going to be T minus 1. Okay, so I bring the X to the other side of the equation and then go T minus 1. So this represents your new u. So this is u right here. And so you can pick whatever values of S and T you want to pick. I'm going to just let T equal S equals 0, and my new u then is going to look like, let's do the X first. I'll have -1, and then I'll have a 0, and then a 0. Now I could let S and T equal whatever I want, and maybe I should have used other letters like P and Q, because it's not the same S and T that we had for the eigenvectors, but we have S and T could be whatever values you want. I got -1, 0, 0, so guess what I'm going to put right up here? I'm going to put -1, 0, 0. There's my new u, and that completes problem number 4, where the algebraic multiplicity is 3 and the geometric multiplicity is 2. So you might wonder, well, what happens, Joe, if the algebraic multiplicity is 3 and the geometric multiplicity is 1? Well, this is an intro class. So a lot of you can turn off the video right now because this is just going to confuse some of you. But here's one where the algebraic multiplicity is 3 and the geometric multiplicity is 1. You have an eigenvalue of 2. And you have, that's what the eigenvectors look like, okay? So there's only one parameter. And so what would this look like? Your solution would look like C1 vector x1 plus C2 vector x2 plus C3 vector x3. So note that you're not going to get anything like this in your homework. But this is for the math majors maybe. So vector x1 is going to be e to the 2t, 1, 0, 0. And vector x2, which is this guy right here, is going to be this. It's going to be t, e to the 2t, 1, 0, 0. And then it's going to be e to the 2t. This is what we usually put in parentheses. I'll put the parentheses there. And then this is your new u. Okay, so here is x3. And you might guess what it is. And so here is, maybe you would put parentheses around there. So here's what the guess would be. T squared e to the 2t. And then this would be 1, 0, 0. And then this would be plus t e to the 2t. Here's your new u. And then you would have plus e to the 2t. And now let's pick a color that I haven't used yet. this guy right here, and this is your new W. Now, you might go, whoa, wow, that's cool, that's what I expected. No, actually this is going to be t squared over 2 factorial. And so it does get a little more complicated if you have 4 by 4 or 5 by 5 and this kind of stuff happens. And so this just kind of shows you that things can get more complicated. How do you find your V, your original V, which is this guy right here? We went like this. We went A minus 2, and I'll put a 2 there, 2I. V is 0. How do you find your new U? You go A minus 2I U equals V. And how would you find your new W? You would go A minus 2I W equals U. And so yeah, is this am I going to write out the whole answer? No, I'm not going to find the U and the W because I don't want to stress people out. But math does get harder. And just remember, this is an introduction class, and I've conveniently skipped any in your homework where it has an algebraic multiplicity of 3, geometric multiplicity of 1. Because, you know, we didn't want to spend another hour discussing the derivation of the factorials, but once again, this math does get a little more complicated. So this completes 9.5 of differential equations. Do your homework. Have a good day.